So now let's get into another example, I guess our very first example that we're going to do together out of this section. And so they're specifically picking a setting where where we have a normally distributed setting. So females have a pulse rates that are normally distributed with the mean of 74 and a standard deviation of 12.5 beats per minute. If one adult female is randomly selected, find the probability that her pulse rate is greater than 70 beats per minute. Well, that A part, as we look at part A, we're selecting one person, so this is really a 6.2 problem. So we got some more practice with 6.2. We know that female pulse rates have a mean of 74, and they're asking for the probability that a randomly selected female has a pulse rate above 70. So from our experience in 6.2, that's not a problem. We need to go look up 70, but we can't, so we're going to go look up its z-score. And as we take a look at 70 minus 74 divided by 12.5, let me see what that is. We get a negative 0.32. So we're going to look up negative 0.32 in our table A2, which is on the back cover of your text, or in the middle as well. And if we look up negative 0.32, we come up with the value 0.3745. And we remember that 0.3745 is the area to the left. Well, we don't want the area to the left. So the probability that this one woman has a pulse rate greater than 70 is equal to 1 minus 0.3745. And if we look at 1 minus 0.3745, we get 0.6255. And that's the answer for part A in number 6. 0.6255. Now take a look at B. B, I've just slid it up to the very top of the screen. If 25 adult females are selected, find the probability that they have a pulse rate with a mean greater than 70 beats per minute. This is what every true 6.4 question looks like. So this is a 6.4 problem. And the reason is we're dealing with a group of 25. Now, we're able to get by with a group of 25 even though 25 is less than 30 because the original distribution was normally distributed. So we're welcome to continue to use a normal distribution. And so if you remember, the first thing that we have to do if we recognize that we're in a group is to realize, well, the mean's going to stay exactly the same. So we're still going to have a 74 right in the middle. They're still asking about 70, but the question's slightly different. What the pictures look exactly the same as you look at them top and bottom, but we're going to get a slightly different value because our standard deviation for the group is no longer going to be 12.5. It's going to be 12.5 divided by the square root of 25. And so as we look at what that is, what 12.5 divided by the square root of 25 is, we'll see that we have a new standard deviation for these 25 women of 2.5. Now everything else is the same. You can see the work that we did before. We're still going to do the same work. We're going to take 70 minus the mean, which is still 74, but divided by the standard deviation that has now changed because we have 25 women, and it's now 2.5. So now I'm going to take the 70 minus 74, but this time divide by 2.5, and I'm going to get a massively different number, negative 1.6. So we do the exact same thing. We go look up the negative 1.6 because that's the value that we're going to get in there. I'll call it 1.60 to remind myself to look it up on the outside of the chart. And negative 1.60 corresponds to 0.0548. And so the probability, and look at the difference in notation, that this group of women have an average that is greater than 70 is equal to 1 minus 0.0548. And what would that be? So if we look at 1 minus 0.0548, now we get something really different, 0.9452 as the answer to B. And so it's much more likely for the group of women to average out to be above 70 because the mean's included in that region. As we deal with groups, they get really, really close. Their average gets really close to the mean. So if the mean's ever included, you get a higher probability. For the individual, it was 0.6255, but for a group of 25 women, it's 0.9452.